Hello.
Hi.
Okay. Hello everyone. So this is my presentation about visual state diagram and how we are using it to do some complex tasks which I usually find very difficult to be done in a ROS environment. So it's making my job very easy and I want to share that knowledge with you. So I'd like you to open this project that I have. And first, let's see the Jupyter notebook. So let's open this Jupyter notebook. Let's shift it to a new screen so we can see it better, or let's just keep it here only. So here you can see that this is like one of the visual state diagram tools which we have. It's a very interesting tool developed by JDE Robots. And before even going to this tool, I'd like you to introduce what is a visual state diagram. So basically, visual state diagrams are various behaviors which are connected together using some transition conditions. They are like many tools like SMAC or the one that Epson showed. And this is another tool which is used to program state diagrams. And since it's doing everything visually, like with a GUI, it's called a visual state diagram. And it's very useful when you want to do many complex tasks where you want to produce many types of behavior. So one kind of behavior can be a robot moving, then a robot can be an avoiding behavior. It can be going to some waypoints. That can be one other behavior. So basically, there are many tasks a robot can do, and the decision to make those tasks happen is done by this visual state diagram tool. So yeah, let's see how this particular tool is very easy and useful for us. So our next thing that we need to do is you can keep this open and we'll open a shell. So you can go under tools and open a shell. And here you will type visual states underscore py. Now you'll have a visual state diagram, but since it's a GUI based tool, we'll have it in graphical tool environment. So you can open it, and I have opened it in a new screen using this icon. So I will get a better space to see things. This is our visual state diagram that we are going to use. And for the first task that we have here, we are just getting an introduction about what is a visual state diagram. So you'll come inside this Jupyter notebook and you'll see this procedure that we are going to follow. I'll go through this activity as it's mentioned here. So you can easily follow me and do this. So our first task is to understand how to put states and transition in this tool and how we can program it using a visual GUI like this. So here you have this canvas where you need to put some states and transitions. And to do that, you go under figures and you select state first. So for we need two states in this visual state diagram. So we'll just put two by clicking and we'll connect them together using this transition. So you select the first state and the second state. And now your visual state diagram is completed visually. So this is our first visual state diagram, which needs to actually transition between these two states that you kept on the screen there based on this clock variable. So what we are trying to achieve is we are trying to achieve 3 seconds of delay between the two states. Like the state 1 to state 2 should take 3 seconds delay and then it should transition to the state 2. So that's what we are trying to achieve here. And later we'll see how it will be useful for our robot. So to actually code this state, we'll go under state 1 and like start the code by right clicking. So here you can see there are two options. You can either program it in Python or you can program it in C++. We prefer Python, so let's see how to do that. So we are using this variable called clock, and we'll just say clock is added 1, and then we are keeping a delay of 1 second. So after every 1 second, it will add 1 to this clock variable. So whatever you put inside the state code, it's basically a loop. It's a while loop which goes on and on until the transition condition is met. So we'll first accept it, and since you actually use this variable clock, you also need to initialize it somewhere. So we'll do that right now. To do that, we go under data, and under variables, you can tell whatever variables you're going to use. So let's say we are using clock, and we can make it 0. So here you are using a global kind of a variable, so you can access it from anywhere. So it's easy for us, and we are starting with 0 value. So after 3 seconds, we'll have clock equal to 3. So what we need to do in transition, we can go inside this transition and code it. And here you can see there are two kinds of transition types. We'll select conditional type for now, and we'll just say if clock is greater than 3, or let's say 2, then return true. So this is basically where it always checks whether the transition is true or false. So whatever the output of this will decide whether it will go to state 2 or not. So when the clock is greater than 2, that is 3, it will go to state 2. That's simple. Now we are done with the coding part, but we need to add some configurations. So the first configuration that we need to do here is, as you can see here, we are using this library called time. So we need to tell this to this project that we are going to use this library. So you can go under actions, and under actions you'll find this library, and you can just write time and press add. So now you are done with adding time library support, and now you have to go to this config file again under actions, and instead of JDE communication we are using ROS node, and you can write in build dependency ROS file. It's basically for generating CMake list, uh, document what you need to add as dependencies. And there is another tab here, that is which topics you want to subscribe and publish. But since we are not using any topics right now, just leave it empty, and you're done. So now you need to save it. Let's make a folder here, and let's name it as something. It's up to you, whatever you want to name. And after you're done saving it, you have to go under actions and click generate Python. So it automatically generates the Python code for it, and you can come back to the IDE and see what happened. So under Catkin workspace, where we stored the folder trial under source, you'll find that this try1.py is generated now. It wasn't there earlier. And here the whole code for the GUI based tool that we used is generated. So it did all the hard work for you, and you just concentrated on what you wanted to get done. So now let's run it. I won't need it for now. So to run it, you need to go to the same folder, and now you need to write this, like you need to call this Python script, which is inside, and then you define the XML also as an argument, and you pass this argument, display GUI equal to true. So once this last argument is true, then you can also see what's happening with your state diagram. We'll just run it now. And here you'll see that after 3 seconds, your state got transitioned to state 2. State 1 got transitioned to state 2. And it was simple for us to design this, right? Yeah. So let's get back to the state diagram and do something more interesting. Let's come out of this and now end this. We ended the state diagram, and now let's open a state diagram which I have created already to like make the process faster, but it's a very simple state diagram. You can see here that the other state diagram will look like this. And to open this, you need to go under the robot motion package and select this start.xml, and you will have this state diagram. So what we are trying to achieve, let's get a step back and go to this screen again. And under simulation, I want you to select the launch file and launch the main launch file here. So we are trying to work on this warehouse robot that we have here. And this is basically the turtle bot which we are using to actually monitor and inspect a warehouse. So this is like a warehouse environment we have created, and these are some packages which are kept on warehouse shelves. And the ultimate aim of this robot is to go along these shelves and inspect where there is a space empty to keep more packages, so that it can report it in a database to the end user that you can keep more things here and reduce the time for a human to go and see it every time. So we are trying to achieve that, to know whether the space is empty or not. And the first activity, the task that this robot needs to do is basically go to various locations, and the second activity we'll be doing later is basically seeing these shells and understanding whether they are empty or not. So to go to various locations, we need to give it basically some endpoints and go ask it to go there. So let's see how we did it in this state diagram that you just opened. So here you can see there are like 4 states. The first state is basically the initialization, where we are going to initialize all the nodes which we are going to use. The second state is waiting for a goal from the user, where he or she needs the robot to go. The third state is following that goal and going to the goal reach state once the particular goal is completed. and then again coming back to the get goal state and waiting for the next goal and following this loop. Right? Simple. So first we'll open this initialization here and code it. I have done some part of it, but I have left very important part for us to understand what's basically the process of initializing the nodes using a visual state diagram. I found a very important library which we are going to use right now. It's called OS library, which will help us in calling some command line commands using Python. And that's how we'll call or we'll initialize new nodes. So coming back to the Python notebook, Jupyter notebook here, uh, yeah, right here. I have written some codes here which we'll need to input. And the first code which we need to input is this one. But since we cannot copy paste it in the GUI, I've also kept it in a gedit notebook. Like you can open it using a gedit. So we'll just write gedit right now. And now you can copy paste it directly in this visual GUI. So whatever you have in gedit, you can copy paste it. And we'll go under Catkin workspace, source, robot motion, and these are the codes that we are going to use right now. So the two lines of code that we are going to copy paste in that area are these. The first line is basically calling this turtlebot navigation gazebo package and launching this launch file, passing this map as an argument. So basically, this launch file is uh, like launching many nodes. It's launching the move based node. It's launching AMCL. It's also like launching the map server using this map file. So all these three nodes are created using this line here. And the second line here is basically opening up the ROS ROS so that we can visually put some goals and see how the robot is moving, analyze it, and see everything in action. So let's copy paste it here. Yeah, take care of the tabs here. It's actually Python only, so you need to keep it as Python. And other than that, you can see that there is this done variable which is false, and later it's made true once this is done. So why this done variable is needed? Because you remember that we were saying the state code is done again and again in a loop. So to prevent that from calling these two commands again and again, we are using this done variable. So it just do it once and then transition to make sure it always stops after doing one. Once you are using this done variable here, and in the transition you can predict what we are doing now. We are checking whether the done is true, and if it is true we are returning true and making it again false. So why we are making it again false? Because we want to use the same variable again in other states to make it only go once, right? So once the initialization process is done, the done becomes true and the transition happens, and now you can go to the get goal state and open this get goal state now, and let's copy the other code from here. here what we are doing, basically we are subscribing to a topic called move based status. Uh, let's just pause for a minute and let me introduce you how we actually subscribe to this topic. So here, go back to the actions and under config file, you can go under topics now. Here you can see that there is a subscriber, right? Basically, this is what I created. It's already available under move based status name, and this is a type. You can select any subscriber that you want to subscribe to by going in this drop down list. All those available topics in your database is shown here. So the one that we need, it's of basically action lib messages, goal status, array type. And let's make it again. So we'll go under action lib. Yeah. So we are subscribing to this topic type, and this is the name of the topic that we are actually using. Move base / status. And when I press add, it will add it. And now you can actually access this topic by this convention. This is like a standard convention. You say ROS node dot move base underscore status, and then whatever uh, sub variables or subtypes you want to use, you can access it using that. So this is the command where we are accessing the status of how our move base is responding. So it's giving some feedback and we are taking input from that feedback. You can remove one of it, so you don't need same copy. And yeah, that's where we actually use this subscriber. And what we did with it is basically we are trying to know what's happening with the move base status, and you can also check it what that actually gives you by going under move base. So there are like multiple outputs that it can give, and you can see that these are the values. So if it actually got a goal, it will be 1, the status, and if it succeeded, it will be 3. So these are the two values we are interested in. So here we are actually checking that status, whether it's 1, then we say it's available for us, and we make done equal to true. And here again in this transition, we need to put that done checking. So I've already kept it here. So if done equal to true, you can make it false and return true. And now you can transition to the next state, which is follow goal. And under follow goal, you can copy paste the next set of code. And I think now it should be clear to you what's happening in this code. You are checking whether the status became 3, and that means you have reached the goal, and you make done equal to true so that you can update the transition. And again, go under transition 3, and you can see we are checking done, and it's done, so we can go ahead. Basically in goal reach, we are not adding any code here. It's just a temporary state to notify that we have reached our goal, but we are waiting here for some seconds. So we want to put like, some temporal wait. We can wait for 2 seconds, we can wait for 5 seconds, and again go to the get goal state. So this is another kind of a transition that you can make directly In the last activity, we actually made a clock with a time library, but you don't need that. You can directly put what delay you want between two states, and if you select the temporal type, this delay will be basically taken, and it's in milliseconds. So after 2 seconds, it will go back to the get goal state, and yeah, that's it. We are done. Now we just need to do one more thing, which is adding the necessary libraries and maybe one variable that we use, which is basically the done variable. I think we already added it. So basically global done equal to false. We are initializing it. And now we can go under libraries and write the required libraries. I don't think we need time, but yeah, let's keep it for future. And now let's first save it. Very important. And now we'll generate the Python, and it's generated. You can see again what's the Python code generated. Your other folder, which is robot motion, and this is the generated Python code. We added these commands here and all those things. So yeah, we are ready to launch it and see it in action. So to do that, let's just remove the gedit and go to the folder where we have Python. The folder name was robot motion, and now you can run it with this. Yeah, basically you must have it in Gazebo first. Don't forget to open Gazebo with the launch file, so it can find the robot which you are trying to use. Don't worry, the overwriting is fine. It's a bug. So okay, this is new where we did it. So maybe we didn't use global somewhere for checking the done. Let's see. This is fine. This is fine. So yeah, this is where we did it wrong. Sorry. So yeah, this is an error. Silly one. So let's generate the Python again, and let's try it now. Okay. Is there somewhere else we did this? Yeah, I think this was an error. I should have corrected. Let's try it the third time. Now, let's go and check in the actual Python. So the benefit of this whole tool is that you can see your Python code that's generated and find out where it's going wrong. So it says it's going wrong on 96th line of the Python, right? Yeah. So let's go back to that and see where this 96th line is. So here in the check condition, you can make comments and save it again, and let's run it. Yeah, it's working. So see, you are able to use the whole code and do whatever you want to do, and now it's working. So we first loaded the Python, uh, sorry, the ROS and all the nodes that we needed, and now it's in get goal state. Now you can actually provide it the goal you want it to go to using your navigation goal, and it should follow it. So it transitioned into the follow goal state, and you can see, you can easily visualize what its status is. It in following goal state, or it reached the goal, or it's waiting for the new goal. And it's easy to debug now, as you saw now. So that's basically the very basic implementation of this visual state diagram. And let's now try to do something complex, although it's not very complex, but really interesting application of this visual state diagram. And let's open a new shell. So this last activity I'm going to show you as a demo. You can see the code in your own time, but since we have some time limitations, I'll like you to open the demo that I already created, like going in file and opening this, and visual state folder here. So this is the end application of the warehouse robot that we are trying to create, and this is the basic visual state diagram here. But there are little more complexity here. We'll see it now. So here you first initialize it just the way we did it in the last activity, and we get multiple waypoints here. Instead of getting just one target, we are getting multiple waypoints so that you can automate the task of going to various waypoints and save it for later use also. And then you start following these waypoints, and this is a condition that is optional, but it's a very required condition in real world, that if the robot is actually going out of battery, it should go to its charging port automatically and go back to its work once it's like done charging itself. So yeah, that's another behavior that robot needs to do in real world, so we added it. And other than that, you can also see that if you double click on get waypoints, you land on this another visual state diagram. So this is basically a sub visual state diagram which is under get waypoints. It's called sub automata. And don't worry, automata is just a term. So it's basically doing all these states inside get waypoints. So these two states are concurrent, the gateway points and whatever is inside it. And basically what is happening here is we are first getting the charging point where we need to go and charge once we are done, once we are out of battery. In our condition, we are actually not checking the battery level, but once all the waypoints are done one time, it goes to the charging point. You'll see soon, and come back after a few seconds. And after we got the charging point, we get the extreme. So what extreme means is, if you come back to the gazebo simulation right here, let me load it again. You also load the gazebo simulation again. We want to start fresh here. So what we want to know is what is basically this extreme point. So here you can see that there are two shells, right? Just two shells. And this area is empty, this area is empty. So we don't want the robot to do the scanning when it is in this area or in this area. It just scans when it is between these two shells. So basically, extremes mean that we are providing it an end boundary that between these 2 points only you do the scanning, and if you are not in between these 2 points, you don't do any scanning. You just follow the waypoints back to the actual shelf area. So that's what extreme means here. And in the end, we have this waypoints, uh, basically what the actual positions what the robot needs to go to, and that's it. So that's basically the get waypoint state. I mistakenly added this transition. You can remove anything by again right clicking it and clicking remove here, and after the get waypoints we are going into this follow waypoint state. This is also having a sub automata, and in this sub automata we are basically having three states, and that means that if you are seeing a filled shelf you be in this state. If you are not seeing a filled shelf, it's an empty shelf, you do be in this state. Like if I am here, it will be in this state, in the empty shelf state, since it's empty right here. If you can see, it's empty. And the last state is basically detecting whether you are in between the two extremes or not. So if you are here, somewhere here or somewhere here, it should be in the not tile state, right? So that's where this visual state diagram helps us, because we can program multiple sub automatas and do complex tasks using it. I can even go inside this and design another automata here by double clicking inside it. Let's remove this transition also. Yeah. So I think the code is already generated, but let's again generate the code just for the sake of it. And let's run it and see it in action. So let's open the shell here and navigate to the correct folder. Yeah. And the name of the diagram is RDC. So yeah, we should use that here. If you don't display GUI, it will run without showing you the actual transitioning by marking them there, but it's running in behind background. So we'll run it. There are some messages which help us in like showing what's happening, but basically we need to see just the visual state diagram here. Where is the visual state diagram? It didn't happen. Did I do something wrong? Let's try again. It loaded everything correctly, but just the GUI wasn't available. So we'll try it again. Now it's available. Maybe the display GUI wasn't made true. Let's rearrange it so that we can view it better. So here is it. And we have it in get waypoints mode. As you can see here, it's waiting for a charging point. You can see, please define the charging point using pose tool. That's how you define a charging point. So we'll use this 2D pose estimate tool here. And let's say that the charging point is here. So we'll just put a pose there and you'll see this arrow here. Now it's waiting for the extremes. So we need to put 2 points, which basically defines the aisle endpoints. And let's see if we can put it right here. It's quite far, but it's fine. Okay. And right here. And now we have to define some waypoints. So you can use again the 2D pose estimate tool here to define the waypoints right here. And this is how you are actually making the path very clear to the robot that you have to go through this path, not only defining the 2 endpoints, but multiple waypoints and giving it an accurate path.
Abhimanyu, just to remind you that you have around 5 minutes extra, and that you should be finishing. Yeah?
Yeah.
Okay, fantastic.
So we are almost there. We just need to put the last waypoint, and this last waypoint you should put as the actual location of the robot, because 2D pose estimate tool is also used by AMCL. If you remember that, AMCL basically gets the initial pose using the 2D pose estimate, and we always want it to start from this location, right? So this is the whole trajectory that we defined for this robot. And the last thing that we need to do, if you will see up here, that you are asked to enter the waypoints and publish true on waypoints added parameter when done. So just need to do that and it should start its work. So we'll say ROS param set waypoints added true, and it started working. And here you can see it's detecting the right and left shelf and basically telling whether it's empty or not. So all these dots are representing the boxes, and if it is seeing a box, it's making this area white, and if it's not seeing a box, it's left black. So there are some like requirement of adjusting the sensitivity of it, but as you will see, once it goes multiple times in this aisle area, it will make more detections and complete the whole process of inspection way better. And you can see here it's following the waypoints, but once it reaches the last waypoint, it goes to the charging state and goes for charging. So yeah, this is the basic demo, and once it's done the charging, it will again go back to the follow waypoints and detect how much area is occupied by these boxes, plot those points occupied by it, and make an accurate description of the warehouse. So you can also see like the Jupyter notebook if you want to follow it afterwards, how to put the waypoints and everything. And that's all. So yeah, Ricardo, I'm done.
Okay, thank you, Abhimanyu. Very good. I'm really proud. Great. So now you can unshare your screen so that we can see your marvelous face.
Yeah, just a sec. How do I unshare it? Yeah.
Okay, perfect.
Hey.
And we're going to start with Q&A.
Yeah.
Because we're short of time, we'll just do 2.
Okay.
So let me have a look. So the first question is, could you tell me the difference, if you can, of between this visual state and FlexB, the system that was talked about yesterday in the presentation?
Like Essen did a very good job describing FlexB, and it's a really nice tool, but it's just that it's not a very easy to learn tool. It's having similar kind of features, but the main difference here is this is like complete GUI based tool. There you need to do some coding first and then add it to the state diagram. And also there you can manipulate some parameters in real time. But here, if you see, you cannot manipulate some parameters in real time. So it's like lacking in that, but always you can like use other tools to manipulate in real time, which is available. So like RQT tools can do that.
Okay.
RQT reconfigure can do that.
Okay. So let's do last question. So the last question is basically all the subscribers that you have in the database and in this UI, can they be updated? So if, for example, you created a new subscriber message, can you update it, or it's hard-coded?
No, it's updated in real time. So it searches the whole ROS directory, and whatever subscribers you have defined, it updates the list using that. So it's not hard-coded, all dynamic.
Fantastic. So we can't do more questions. So thank you very much, Abhimanyu. Really, it was a pleasure.